Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Advanced Fortran programming. Now, in this tutorial, we will be looking at one interesting concept that can be adopted in Fortran, especially for functions and subroutines, called as dummy variables. Now, these dummy variables are not similar or not exactly the same as that of the optional arguments, as that of the optional variables or arguments. They are entirely different. Okay, now using dummy variables, uh, you can use some kind of a recursive kind of functions, recursion like operations using the dummy variables to make certain jobs nice and easy. Well, you may not understand what I speak right now, but if I go through the program, you might understand this nicely. Okay, what I have here is that this program will calculate, will do options, two things. First, it will define, we're defining a function that will calculate the integral power of certain variables. Suppose if you want to calculate the fourth power of some value, like sixth power of some value or something of that sort, then it is possible. Okay, then this function is, and that too on the positive side. I have to mention that positive integral power of the function. This function will do it nicely. And in the second function, okay, we in the second function we will be calculating the value of a polynomial at x, at some point x. Okay, now the program name is dummy underscore vars, and we have an implicit none. I am setting an integer p equals 3 and a real value v equals 3.0. This can be 2 or anything, that doesn't matter. Okay, what we'll be calculating is that the third power of we will be this power will be actually v power p, simple as that. Okay, and then these are for the first function, the positive integral power. For the second function, okay, we need two more. I'll explain. This line is an external attribute, is where we indicate the definitions of power and the poly. Okay, this power is nothing but a power function that we define over here, and this poly is nothing but a polynomial function that we define over here. I'll come to that in a minute. Okay, now what I do is that here in this line I set the value of x to be 5. I set a value called as x and set to be 5, and poly underscore val will have the polynomial value at the end. Okay, and finally, not finally, we are going to define an integer parameter called as n equals 2 here, and that value will be used to define an array, and this array has indices from 0 to n. So this is a three valued array, a three valued real number array. Okay, and what we are going to do is that we are going to set the coefficient of a to be 1, 2, 1. Okay, what this a is going to do is that a will have the coefficients of the polynomial. Okay, now this 1 to 1 is actually this, what I meant in this in my program is that if it's a is 1 to 1, then it actually corresponds to the coefficient of 1, 2 and 1, 2 and 1 here. So this actually corresponds to 1 plus 2x plus x square, that polynomial. Suppose if we have another value, something of that, if you want another value at the right, we add one more value at the right, then that value will be the coefficient of the x cube, and the other value after that will be the coefficient of x power 4 in the polynomial. Okay, so this can be plus and minus, no problem. Okay, now if I for this set of three values, it represents the polynomial 1 plus 2x plus x square. Okay, and this value, and the value of this polynomial at x equals 5 is 36, because it's, if you guys notice, this is nothing but x plus 1 square identity of polynomial. So if x equals 5, then the value of this polynomial is actually 6 square, so 36. So it's simple enough. Okay, and then I call the power function over here and the poly function over here, and I'm printing the power p of v is this, the coefficient of the polynomial here, and then the value of the polynomial x polynomial at x equals x is this value. I'm going to print the value here, and I'm ending the program. And now let's look at the function parts of it. Now this is where everything goes interesting. Now what I do is that I'm not doing any recursion over here. I'm not going to do any recursion over here. What I'm going to do is that, observe, initially I get the value n as an intent in, okay, and I get the value x just like that, just like a usual function, okay, and using the value of n, I define the size of the matrix, size of the array A. Perfect, fair enough, no problem. Now in the integer, I define a new integer for me, I call as I, nothing much. I set the value of poly to be 0 initially, and now this is where everything becomes interesting. I set a do loop that varies from 0 to n, okay, and I set poly to be equal to poly plus a of I star x power I. Now what this will do, since poly is 0, this will calculate a1 a0 plus a1x plus a2x square plus a3x cube and so on and so forth, like that, with the indices matching the subscript of a0, a1, a2, a3 and so on perfectly. But the interesting part of this function is in this function call is that I'm using this function call here and I'm using the function call here, but I'm passing it without any arguments. Okay, that is the specialty of this function. And if you guys notice, because I passed this in this way, okay, what happens is that when this function is called on itself without any arguments, now here this function is calling itself without any arguments here, without any arguments, okay. So as if, now what this means is that x becomes something like a dummy variable. So only when the first time it is being called, x is called as a proper variable, and even a, the entire array is initially called as a proper variable. But after in this do loop, these are called as dummy variables because I'm not passing these variables. So what happens is that when this kind of a call happens every time, okay, x remains as it is, the value of a remains as it is, okay. Only the index positions are different index positions are occupied here, are used for every do loop. Ultimately what happens is that when I use this polynomial function, okay, the matrix, the array A remains preserved, okay, and the value x also remains preserved throughout this internal recursive call, okay. And if you guys notice, I did not use any recursion over here. This is an advantage of dummy variables, okay. Now in this example, x and a, they are dummy variables, okay. And if you guys notice, you can make an array also as a dummy variable, not just a single value but even an array as a dummy variable. So what happens is that this will initially be 0. First, in the first iteration, it will calculate a0, which is a0 times x power 0, so this will return only a0. In the second time, it will calculate a0 plus a1 times x. The next time that sum plus a2 times x squared, then a3 times x cube, a4 times x power 4, and so on and so forth, depending on the value of n and depending on the value of a, just like that. It just goes on. So ultimately it will calculate the value of polynomial, because in all these times the value x is known and it's being preserved and it's being utilized utilized as if some kind of a symbolic expressions kind of a thing. So it's preserved over here. So this works fine. Now let's look at the power function. This power function is again an indication of dummy variable, but this is rather a simple function wherein I get the value n, I get the value x, okay, and I get an integer I set the initial power value to be 1, and what I do is that I run this in the reverse order. What I do is that even if you don't mind in the reverse order, even if it is forward order also, it doesn't matter actually. What it does is that it just calculates x times power. Okay, so initially the power is 1, so it will be x into 1, so x. Next time it will be x into x, so x square. Next time it will be x times x cube, x square, so x cube. Next time x times x power 4, x cube, it's x power 4. So ultimately this value gets repeated again and again in the continuous chain of multiplication, and ultimately you will get x power n as the output. X power n as the output at the end of this do loop. Okay, and that value gets, and this value this value over here gets printed over here. Simple as that. Alright, now let's enough of me talking. Let's run this program, compile, build, and execute this, and there you have it. The power 3 of 3 is 27. Because this, what I mean is something like the third, you can, if you want to read this properly, you can say something like the third power of 3 is 27, or else 3 power 3 is 27. Okay, and similarly the coefficients of the polynomial are 1, 2, and 1. Okay, which is what I wanted here. It's actually printed, and the value of this polynomial at x equals 5 is 36, because it's quite evident because this polynomial is actually x plus 1 square, so x is 5, so the answer is actually 5 plus 1 square, so 36 square, so 36. So it is quite easy to calculate. Similarly, let me do a little trickery, and let me make this 3 here. Okay, and here let me comment this out. Okay, let me put the value a equals 1, 3, 3, 1. Sorry, 1. Okay, this will be 1 plus 3x plus the 3x power 2 plus x power 3, which is nothing but your x plus 1 cube polynomial. So value at x equals 5 is 6 cubes, so it's 216. Okay, now let's check this out, and before that let's try this to 10. So the third power of 10 is 1000, so this should work out fine. Okay, so let me check this out. So if I were to compile, build, and execute this, yeah, perfect. The power 3 of 10 is 1000, which is fine, and the coefficients of the polynomial are 1, 3, 3, 1, so it's a polynomial of order 3, degree 3, so you have an x cube here. So the value of the polynomial at x equals 5 is actually 6 cubes, so 216, and there you have it properly and nicely. Okay, now this is the advantage of using dummy variables. So instead of using subroutines, sometimes for all the conditions, this kind of option may be used accordingly instead of using a recursive function or recursive subroutines. Okay, and if you guys notice, using this option you can write the factorial of a number also. Want to try? Okay, let's do this. Okay, let's do this. Okay, let me define an integer. Let me define an integer of type 8, and let's say f1, and then fact1, and let me define this as integer type 8 comma external, and then I use fact function, simple fact function. Okay, now f1 equals 5. Okay, so fact should be equal to 120, because fact1 is actually the factorial of this function. So let's write it over here. Fact1 is actually fact of let's see, fact of f1, simple. Okay, now let's print it over here. print the factorial of f1 is comma fact1. Okay, now let's write the function over here. Let me put this at the bottom. It's integer, right? Integer type 8 function. What did I keep in the top? Fact. Okay, fact. I pass only x over here. X. Okay, let me pass in, so doesn't matter. Okay, and end function fact. Okay, and then I type implicit none. Okay, and integer of kind 8. I'm going to get the value intent in. So intent in. So what this will do is that we'll get the value n. Okay, and okay, let me see. Integer 8 comma I. Okay, this is a local variable I. Okay, now I'll set fact to be equal to 1 initially. Okay, and now we need a do loop again. Do I equals 1 to n fact equals fact star I and do. Alright, simple enough. Okay, now what this function will do is that it will takes n as a dummy argument once again, but this n gets used over here. Okay, so when I run this function, when I run this part of the function, it does not take the value n, so it treats n as a dummy argument. It just multiplies again and again with I every time. So initially I fact is 1, so it is 1 times 1, so 1. Next value of I is 1 times 2, so 2. Then next value is 2 times 2, so 4. Next time it's 2 times 2 times 3, it's 6. Then 6 times 4 is 24, and then 120 of that sort. And if I keep since I kept n f1 equals 5, this should return 120. So if I were to compile this, not bad, no error in the first run. Build this and execute this. Perfect. This is exactly the uppermost result is exactly what we saw, but this result, what we saw here, is classic. It's simple, extremely simple. Now imagine instead of doing a recursive function, this is much easy, isn't it? Okay, using dummy arguments, this is much easy. Okay, and we get it right. Suppose if I were to set this to 10. Okay, compile, build and execute. Compile, build and execute this. Okay, I think I didn't save this. I think I didn't save this. Okay, now if I were to compile, build and execute this. I think I placed the wrong value over here. Something. Okay, I think I'm not compiling properly. Build and execute this. It's still showing 5 equals 120. Why does it so? Why does it? Okay, let me. I think it's in the desktop. Let me just delete this dummy vars and this object file also. They might be causing some issues. Okay, now if I were to compile, build this and execute this, the factorial of 5 is still 120. Why is that? Oh, did I change the wrong value over here? Oh shit, sorry, I'm extremely sorry, I didn't notice. This should be changed. I was changing the wrong direction. Sorry, I was changing the wrong place. So if I were to set this to 10, why not? let's set the value to be 10 here. So this should return, since if it's x equals 10, then this polynomial should return, the third order polynomial should return 11 cubes, so 1331. So let's check this out, compile, build and execute this. Yeah, perfect. It returns the 10 factorial nicely, and then it returns the powers nicely, and even the polynomial nicely. Perfect. Now that's all I have for you guys in this tutorial. Thank you guys for watching, and I'll see you guys in the next tutorial. Hope you guys learned something in this dummy variables function. Thank you.